Hello, good morning to everyone. Myself, Dr. Mahadev Unde, Professor in Electrical Engineering, Zeel College of Engineering and Research, Pune. In this video lecture, we are going to learn the effect of loading on alternator and the theory about the voltage regulation. Now look at this circuit diagram. The alternator, it has a main two parts, the stator, which consists of the armature winding and which is generally star connected in order to have less insulation level. And the another part is the rotor on which field winding is placed and which is generally excited by DC source as shown. The third element is here the prime mover, which rotates the alternator at an synchronous speed. Now when the excitation is increased, it will develop the voltage and go on increasing the excitation till you will get the rated voltage. Now put the load or connect the load to the three terminals of the alternator. The fourth terminal neutral may not be available or may be available, and the load may be a three-phase star connected or delta connected. Once the load is connected, the alternator starts delivering the current. Then we can develop the relations from this. Now here, by keeping the speed constant and the excitation constant, if we load the alternator, its terminal voltage falls because of the following reasons or because of the voltage drops taking place in the various parts as shown. Now the voltage drop is due to the armature resistance, that is IARA. The next voltage drop is due to the leakage reactance, that is IAXL, and the third voltage drop is due to the armature reaction reactance, IAXL. Now the combination of this XL, leakage reactance, and the reactance due to armature reaction is known as synchronous reactance. Thus the synchronous reactance XS equal to XL plus XA. Now see the equivalent diagram of the alternator. Now see, here it is the EMF generated is the E0, that is the no load voltage, and RA and XS, these are the winding parameters, and the combination of this armature winding resistance RA and the synchronous reactance XS is nothing but a synchronous impedance ZS. And here are the two terminals where the voltage available, say it is drawn per phase basis, and therefore it is shown VPH here. And this is the armature current. Or if the load is connected here, when the load is connected at the terminals, it starts delivering the load current. Okay, and thus we can develop the relation between E0 and VPH as shown. Now see here, the E0 equal to generated EMF equal to VPH, that is the terminal voltage plus voltage drop in armature resistance and synchronous reactance, that is IA into bracket RA plus J XS, and therefore E0 equal to VPH plus IA into ZS, where ZS is the synchronous impedance. Now at no load, when there is no load, the IA equal to 0, and therefore generated EMF E0 equal to VPH as shown. And remember that these relations are the phasor additions and not the arithmetic one. Okay. Now let us proceed further. Now what is the voltage regulation? Voltage regulation is nothing but a rise in voltage when full load is suddenly switched off, keeping the field excitation and speed constant, divided by the rated terminal voltage at a specified power factor. Thus the voltage regulation is nothing but no load voltage per phase minus full load voltage per phase divided by full load voltage per phase multiplied by 100. This can be written or shown symbolically. The percentage voltage regulation is equal to E0 minus VPH upon VPH into 100, where E0 is the no load voltage per phase when there is no load at all, that is load is switched off, and VPH is the rated voltage. Now see, the alternators are always designed to give a certain rated terminal voltage when supplying a rated current a rated load at a specified power factor of the load. Therefore, the load characteristics of the alternators are as shown in the figure. Now here on the x-axis there is the load current on x-axis, and y-axis represent the terminal voltage. Now say the full load current is OB. The full load current is OB, that is the rated current, and this at this rated current the terminal voltage maintained is the BP, or say the point P is the operating point. Point P is the operating point, and at this point P the rated terminal voltage is BP, and that is equal to AO. That is equal to AO, and this is at the rated current OB. The same things are shown here if you observe carefully. OA, this OA equal to BP equal to full load voltage VPH, and this OB equal to rated current or full load current. Okay. Now if this full load current or when this full load is switched off suddenly, what happens? This rated current goes to zero. This full load current goes to zero. That is at the origin, and the curve trace for the lagging power factor is like this at the point D, and therefore OD represent the no load voltage. OD represent no load voltage EPH, means per phase at a lagging power factor. See, everything is here on per phase basis. Therefore, OD represent the per phase voltage at a lagging power factor at no load. Similarly, OC represents, see this curve is for the unity power factor. So, OC represent the no load voltage because it is measured at the origin, and here the load current is zero. So, it is the no load voltage per phase at a unity power factor. OC represent no load voltage per phase at unity power factor, and finally OE represent no load voltage per phase at a leading power factor. Now question is for the lagging power factor, why this no load voltage is quite larger than the rated voltage BP? The reason is the no load voltage is OD, and when the load is increased, its terminal voltage falls and goes to P, that is BP, because of the demagnetizing effect of the armature reaction. Because of the demagnetizing effect of the armature reaction, the terminal voltage falls. Now in the unity power factor, this fall in terminal voltage means the no load voltage is lesser than the which is at the lagging power factor because of the distortion effect or cross magnetizing effect of the armature reaction. Now whereas for the leading power factor, the no load voltage is OE, and as we go on increasing the load, the terminal voltage increases. Then this happens because of the magnetizing effect of the armature reaction. Because in this case, both the fluxes, the flux due to main feed and flux due to armature current, both assist each other, and therefore as the load current increases, the voltage also increases. Okay. So in this way, we have studied the characteristics of the alternator. Now for example, let us have the example, what would be the voltage regulation at a lagging power factor. See, at a lagging power factor, no load voltage, we have already studied the definition of the voltage regulation, that is the no load voltage per phase minus full load voltage per phase divided by full load voltage per phase multiplied by 100. So what is no load voltage per phase? That is nothing but OD. See, the power factor, for example, the voltage regulation at lagging power factor curve is this, and OD is the no load voltage per phase minus OA. OA is nothing but the full load voltage per phase divided by full load voltage per phase multiplied by 100. So this is the voltage regulation of the alternator at a lagging power factor. Remember that this voltage regulation is positive because this OD, no load voltage OD, is quite greater than the full load voltage OA equal to BP. Okay, that means the numerator is positive and therefore voltage regulation is positive. Now let us see, similarly we can obtain the voltage regulation at a unity power factor as well for the leading power factor. Now observe here at a unity power factor, the percentage voltage regulation is OC minus OA upon OA into 100. Here also OC is greater than OA. That means numerator is positive and therefore voltage regulation is positive. Now similarly we can obtain the voltage regulation at a leading power factor, and which is given by the percentage voltage regulation equal to OE, that is the no load voltage per phase minus OA divided by OA, where OA is the full load voltage per phase multiplied by 100. Now we have observed that this OE is less than OA. OE is less than OA and therefore numerator is negative, and therefore we can conclude that the voltage regulation is negative at a leading power factor. Further, I would like to state that the zero voltage regulation is possible at a leading power factor. Okay, so in this way, see, thus the voltage regulation is positive for lagging power factor as well as unity power factor, whereas it is negative at a leading power factor of the load. But remember one note that, remember this one, this is the important note: the rise in voltage when full load is suddenly switched off is not equal to fall in voltage when full load is applied. Remember these things, and in this way we have obtained how the alternator terminal voltage decreases when it is loaded, and what is the theory of the voltage regulation, the definition of voltage regulation, and regulation at a three power factors, that is lagging power factor, leading unity power factor, and leading power factor. It has been observed that voltage regulation is positive for both lagging power factor as well unity power factor, whereas it is negative for a leading power factor. It is also possible to have a regulation 0 at a leading power factor. We will stop here. Thank you very much.